So it turns out that I've spent quite a while working in C#, and I thought I had a pretty good handle on what the type system was and how it worked and the differences between value types and reference types, which in a sense was C#'s USP. And then in 2019, they went and changed it. And then in 2020, they changed it again. So C# 5 and 6 introduced two new ways, no less, of creating your own user-defined types, and throws it all into disarray. So I started looking into why and figuring out what was going to be good and what was not quite so good, possibly not as well thought through as they thought, perhaps. So over the course of the talk, we're going to look at the family of value types in particular, but we're going to look at classes and reference types too, because it doesn't make sense to look at value types on their own. It's much more interesting to compare them with the other kind of type. And why that matters. What is the point of value types in C#? And what are they good for? What are they not so good for? Why you would and wouldn't want to use one. So to an extent, comparing their characteristics, or sort of comparing all of the characteristics. So this isn't a showcase for the newest C#, which at the moment is C# 10, although they do seem to be upversioning about every 12 months at the moment, which makes it really hard to keep up. But some of the syntax is going to be new C#, so raise a hand if it's unfamiliar and it's really not obvious or I'm not explaining myself very well, what's going on. But we will start with what I hope will be fairly familiar as the humble struct, the basic value type in C#. And that could be bigger, couldn't it? So we've got a struct type, user-defined type with 3 mutable properties, and it's about as simple as it could be. I mean, it could have 1 mutable property, but then that would make it even harder to see on the screen. And really what's interesting about it is that there is a compiler-defined constructor, sort of, but we normally create one of these with what's known as object initialization syntax, where you create an object and then assign values to each of the properties in turn. And the other interesting thing about it is, being a struct, it's a value type. It has copy by value semantics, which means that if we create 2 instances that have the same state, they compare equal when we use the equals method. Everything okay so far? Nods all round, great. The interesting thing is comparing that with a class. So the only thing that's changed here is the class keyword instead of the struct keyword. And classes are, excuse me, reference types. The test is identical to the previous slide. So we're creating 2 new instances of a color using object initialization syntax, which we can do with classes as well as structs. But this test fails because classes have reference semantics. So you create 2 instances with the same state, but reference semantics means that equals returns true when you have 2 references that are to the same object. So that's the big difference. So still all okay? We're on familiar ground. Good, good, good. So the equals method is the thing that defines how these bits work. And so C# has a common type system, or a so-called common type system, where everything inherits from object, and object defines an equals method, amongst other things, and that's effectively how it's implemented. It's a reference comparison between 2 reference variables. So we've got here a couple of things going on. The most obvious, I suppose, is that there are no curly braces. So I'm using here expression-bodied syntax, which is relatively new. So it just uses the lambda operator and get to use that because it's a single expression that's returning a value. So the result of calling equals is just the result of that expression. Also, fairly recent are nullable reference variables indicated by the question mark, which is quite good. Is it an object or is it null? So this is a nullable reference, and that is explicitly saying that we expect the other parameter to possibly be null. We don't have to test for null here because we're not trying to do anything with it. All we're saying is it the same reference as the this reference for this object? So if it's null, it won't be because this can't be null. I think that's everything. Is anybody really unfamiliar with nullable references or non-nullable references? It's not going to be really important for the rest of the talk, but I'm happy to talk about it. No? Okay. Questions as we go is fine, by the way. Because equals is defined on the object base class and everything inherits from objects and therefore inherits that implementation unless it's overridden, we can compare any two variables, regardless of their type. So here we're comparing an orange and an apple, just because. But one of them is color and the other one's a string. They won't compare equal because the two references can never be to the same instance. But syntactically, it's perfectly valid. The program will run and it'll just never compare equal. So that's kind of quite an interesting aspect of having this common type system, right? It's that this valid syntax of being able to compare any two variables matters because you have to then think about what the semantics of your program mean in that case. And here the test passes because we're asserting that they're not equal and they can never be equal. So if we want a class type to have the kind of the equals by value comparing state, then we have to override the equals method that's inherited from object. So here we've created a method that overrides equals in a way that makes sense for the color type. So what we want to do really is when somebody calls the equals method, we want to compare the values of the properties rather than whether the references are to the same instance. Because it's a class and a reference type, it can be null. So we have to manually check that it's not null. And we also want to make sure that the types match because normally instances of a derived type will not compare equal to instances of a base type. It very, very rarely makes sense for that to be true. So there are a couple of other new things going on here. The first one, again, it's an expression-bodied method because I'm making use of the short-circuiting semantics of the logical or and operators, which short-circuit as they go. And with a bit of careful ordering of those different bits of the expression, we can avoid parentheses because of operator precedence, but hopefully it's not too obscure. And that first line in the equals method is really just it's an optional optimization, because if the two references are the same, then they must have the same state, because they're the references to the same instance. So if that's true, then we can just bail out early. On the second line of the equals method, that obj is color other. This is it's a type pattern combined with a declaration pattern. So if obj is a color or a type that derives from it, then, and is not null, by the way, then the other becomes a variable of type color and is upcast effectively to that correct reference. Because the is type pattern will also match a derived class, we still need to manually compare the results of calling get type, which if you have a sealed class, you don't need to do that because you can't inherit from a sealed class. So we'll get to the sealed class in a moment. But if all of those aspects of equality match, then we carry on and we can compare the values of all the properties, and if the property values are all equal, then the two color instances are equal, irrespective of whether they're the same, or references to the same object. So we have value-based equality for a reference type. And We have the same test at the bottom, creating two instances of that, and that test now passes where previously it failed, because we're comparing the state. Overriding the equals method, the compiler complains if you don't also override get hashcode, so there is a fairly intimate relationship between equals and get hashcode, because get hashcode is also provided by the object-based class. And because get hashcode is always available and equals is always available, then for safety, if you override one, you should override the other to basically perform the same check. Here, I'm just using a built-in library function, which is a perfectly adequate, quite well-distributed way of creating hash codes from the three properties. But the important thing about it is that two color instances that compare equal with the equals method will have the same hash code. That's kind of the takeaway from that. I'm not going to really talk about why here, but it's important for storing things in hashed containers. And so, same test now passes because we're comparing state. So we can forget about get hashcode for a bit. So value types should be sealed. If we're implementing a type as a kind of that has value semantics for the purposes of equality, then it should really be sealed. It doesn't make sense to derive one value from another. It's very difficult to get the semantics right. And it rarely makes sense, as I said before, for comparing instances of a base with an instance of a derived. They should very rarely compare equal. Can't, off the top of my head, think, in fact, not even off the top of my head, spent quite a bit of time thinking, trying to come up with a compelling reason for doing that. Never been able to do it. Structs in C# are implicitly sealed and don't inherit from anything other than the built-in value type class, which provides these value semantics that we just explained. So because we're doing it as a class, we explicitly seal it and implement the iEquitable protocol, which is a built-in interface type which gives you a type-safe equals method. So instead of taking an object reference, it takes the color reference, which allows us to avoid the explicit check for the type, because we're also sealing the type, sealing the class. So comparing the two references in this one, it's basically that top line in the equals method is, again, it's that optional optimization for if you've got two references to the same instance, then they can only ever be equal, whether by state or by reference. But instead of having to check the type with the type matching pattern, we're just using another quite new feature of the constant testing, constant matching pattern. Something like that. Anyway, it's about matching constants. Is and is not are important, because rather than saying if obj equals this, if we then go on to override the operator equals, which we can, that's a recursive call. Would normally, in a normal implementation, would end up infinitely recursing. Using is not and is null pattern, constant matching pattern, that will never invoke a user-defined operator overload for equals. And it's always a reference check if it's in a reference class. Comparing value types with null doesn't make sense and is usually disallowed by the compiler. The other interesting thing about this, going back up to the top, is we've made the properties immutable. We've lost the public static accessors. Value types, it makes sense for them to be immutable in most cases. Any disagreement there? Go on. Oh. Good, fine. Value types are sealed and they're immutable. So that means that we introduce a constructor to create instances. So we can no longer use the object initialization syntax because that requires publicly mutable properties to do that. And again, the constructor is another expression-bodied constructor, that's an even newer feature than just expression-bodied methods. That was introduced in C# 9, I think, where we can use the same syntax for a constructor as long as it is a single expression. And to enable us to make it a single expression, we've got tuple assignment. So another quite new feature, forget which version of C#, maybe 8, introduced a value tuple. So C# had library support for tuples, which was a bit clunky, and introduced in probably C# 4 or 5, and they were unsatisfactory for a variety of reasons. They replaced it quite recently with a value tuple, which allows us to use what I hope is fairly familiar tuple syntax, so a bag of values in parentheses. It's common in several languages. But that tuple assignment, so we're basically creating a tuple of the 3 properties, red, green, and blue, and assigning it to a tuple made up from the RGB parameters to the constructor. And the compiler turns that into a very, very efficient assignment to each of the backing fields for those properties in turn. So the compiler gives special preference to constructor tuple assignment, and it is as efficient as it could be. So it's basically generating the same code if you had private fields for red, green, and blue and expose those by properties and you assign them manually yourself. So it's quite clever in that respect. So that's kind of one example of how the compiler is generating code on our behalf and making code easier to write, easier to read, and hopefully, a little bit more straightforward to understand, as long as you understand the syntax, of course. And then, so the type safe equals method is the implementation of the IEquitable protocol. I call it a protocol because it's used under the hood in lots of places. It's basically an indicator to the compiler that your type has this type safe equals method, and the compiler jumps through hoops, and the runtime to an extent jumps through hoops to directly call that if it can. So if you've got 2 variables of type color rather than one object of type, that's a variable of type object comparing with the color, you'll end up calling the type safe one as long as the 2 variables are that more specific type. But we still override the equals method inherited from object to handle the case where you've got an object reference to a color that you're trying to compare. And that uses, again, expression-bodied syntax to pass that comparison off to the IEquitable implementation. And then get hash code is exactly the same as it was previously, just using the same idea. So the type pattern is occurring also in the override of equals here. And this has been a feature in C# since the very beginning. This is not new. And all we're saying here is that if obj isn't a color type, then the null reference it'll evaluate as null. And so null will be passed to the type safe equals method. And that's the only other interesting thing to think about it. But this is really the canonical way of implementing value-based equality in modern C# for a class type. So it's pretty straightforward, but it is a reasonable amount of typing. And then, as I say, we can also override the equals, equals, and not equals operators for our type. And these, I've deliberately gone a little bit more arcane with these. These aren't particularly new features, but they've not been there since the very beginning. We've got, in the equals, equals operator at the top, the left question mark dot equals is a null conditional operator. So the equals method will only be actually invoked if left is a non-null reference. If the left reference is null, equals doesn't get called. It hits the right-hand side of the null coalescing operator, which is double question mark. So double question mark, basically, if the left hand of it evaluates to null, then the right hand becomes the result of the whole expression. So if left is null and right is null, they are equal, otherwise they're not equal. Any questions about that? Does that make at least some sort of sense? So that is slightly arcane syntax. Implementing not equals in any way that would not produce the opposite result to equals equals is frankly rude. It's possible, so the compiler insists that if you overload operator equals equals, you also provide an implementation of not equals. It's one case where the compiler will not generate that for you, so you are allowed to implement not equals any way you like. Please don't do that, ever. It will cause much confusion. The usual implementation of not equals would be to invert the result of calling equals equals. What I'm doing here is I'm inverting the expression that I use for equals equals because it just avoids the extra method called via equals equals, which is just eventually going to call the type safe implementation of equals that implements the equitable color interface. And in the test at the bottom, we assert also that we've got two color objects with the same state, and we assert that they're equal with equals equals, and they are, and all's good. Structs, the implementations up to this point are almost identical except for the checks for null, because struct instances cannot be null. And in particular, the implementation of equals equals and not equals in this case would be much simpler because they can't be null. So it just becomes return left dot equals right. So it's much simpler for structs. So that's one reason why structs might be a good choice for implementing your value types rather than jumping through all the hoops to implement them as a class. But, there are other metrics to consider. So now we get to the new stuff, the really new stuff. C# 9 in 2020 introduced records, which was, as far as I understand it, Java feature envy. So Java introduced it about a year or so prior, and I'm fairly, I don't know for sure, but I'm pretty sure that they nicked it from one of the functional languages or another. And its purpose is to provide a simple way of having value-based equality implemented for your class by the compiler. So here we've got a sealed record called color, where we have the same constructor as before, 3 immutable properties as before, but we don't need an override of the equals method, an implementation of equitable, get hashcode, or the operator overloads. The compiler literally generates those for us. And this is probably as good a time as any to mention structs in this regard. So structs, they have a base class called value type, which implements equals in a way that provides value semantics for structs. And routinely, what that means is it uses reflection to figure out what the values of each of the fields of the struct is and does the comparison. It can't just do a bitwise comparison because any of the fields of a struct might itself have an overload of the equals method and that defines what equality means for that type. So it's quite important that the equals method is called if there is one there. There's a very narrow set of circumstances where the comparison can be a bitwise check, literally a memcomp in C parlance, but it is very, very narrow. And it basically means that your fields are all ints. So it would probably work for color. It probably would be an efficient comparison and not require reflection as it happens. The generated code for records is done differently. It is generated at compile time based on the type and number of the fields that you define for the record. So the compiler understands all the bits you've done and will generate pretty efficient implementations for the equals method and for the operator overloads. Got some examples in a minute. But the point being that a record compiles down to a class The compiler creates a whole class, effectively. It's not just equality. There are a few other methods that it injects for you as well. Pretty printing for toString, for example, and a couple of other bits and pieces. But the most important thing about it is that a record type has value semantics for the purposes of equality. And those value semantics are provided by the compiler in a pretty efficient manner. So it's less typing, much less typing, in fact. Now, there's more to programming than typing, but, it's a thing. Having to type too much can be a bit of a bore. So along with records came what they termed positional records. Same type, the same color type here written as a positional record. It looks like that. It's exactly the same. The compiler generates all of the same bits and pieces, along with basically the constructor that we provided and the properties themselves. Because it's a sealed record, those properties are immutable. They're not publicly mutable. And the positional parameters to the type, as I refer to it, red, green, and blue, correspond to the parameters for the constructor. So I'm using keyword arguments only to highlight the fact that the names of the parameters in the constructor match the positional arguments given to the type. We can compare with equals equals, and they compare equal according to their state. The named properties, red, green, and blue, again, generated by the compiler, highlighting here that they are those names and that they do compare equal because we've assigned values to them in the constructor. Hopefully there's nothing controversial about that. And there is one other thing that is quite interesting about records, which they've called non-destructive mutation, which is a somewhat peculiar name for a variety of reasons. So it certainly doesn't destruct anything, and it certainly doesn't mutate anything either. What it's really doing is giving you a copy by value semantics for what is ultimately a reference type. So when records compile down as classes, so if we have two variables of our type color and we just assign one to the other, we end up with two references to the same instance. And if we could make any changes to that instance, they would be reflected in both because the instance is being aliased by two references. Here, hopefully you can see that, we've got something that's a bit like the object initialization syntax, but with a with keyword. So what that means is that we're creating a new instance of color using an existing orange record instance as a template. And then in this case, we are assigning different values for the red and green properties and leaving the blue property as it was in the original orange variable. The tests at the bottom I don't know how I've ended up with that test. I think I've got a mismatched variable naming going on. Oh no, I've still got orange and text at the top, that's it. So we're asserting that orange still equals to text, they still have the same properties, but that orange and green are independent references. So green is a whole new instance. So we get the value semantics for equality and something like copy by value semantics for records. The with syntax is a useful way of being able to take an existing variable as a template for a new one and give it new properties. And then, so C#10 introduced record structs. And the only difference now is that instead of being just a sealed record, it's a record struct. So classes can be sealed, but not read-only. Structs can be read-only, but not sealed, because they are implicitly sealed. Where the compiler generates a class definition for, if you create a record or a positional record, the corresponding code that gets generated by the compiler for a record struct is a struct. So a true value type. And this has there are a couple of interactions here that are a little bit interesting. So if I go back a slide, one of the characteristics of classes that's always been true in C# is that if you write your own constructor, any kind of constructor, the default constructor is hidden, or rather it's not generated. So you cannot default initialize an object of a type that has any user-defined constructor, unless that user-defined constructor takes no parameters or has all optional parameters, but I don't even want to go there with this. Struct types always can be default initialized, irrespective of whether it has any user-defined constructors. One of the outcomes of that is the positional record here, the compiler has generated, so it's not a user-defined constructor in the sense that the compiler generated it, but in terms of default initialization, is treated as if it were a user-defined, it is a custom constructor. So we can't default initialize an instance of color because the compiler is effectively has been prevented, or it hasn't generated a default constructor. Not so for structs. They can always be default initialized. So this is an interesting playoff between records and record structs that it's just, really it's something to be aware of, but we can create a default instance of the record struct color where we couldn't when it's just a plain record. Another consequence of that is that the object initialization syntax makes sense for record structs in a way that it can't for records. So object initialization is most commonly used in this sort of syntax, which doesn't explicitly say that a constructor is occurring, even though it always does. So here, the new color with curly braces using object initialization, before the curly braces happen, a default instance of color is created with the default values for all its properties. And then the properties are given new values. But when color was just a record, there is no default constructor, so that syntax would fail to compile. You have to call the constructor, which you can before the curly braces. So, but you call the constructor, assign values for all of the parameters for the constructor, and then, well, the object initialization syntax is irrelevant because you might as well just use the constructor as we do to initialize orange here. So we still can use the constructor, but the object initialization syntax makes sense for record structs, but won't compile for records. Unless you go on and define your own constructor, which we did on a previous slide. And you can create your own constructor, in which case the compiler won't try to generate one. So that's a quick overview of records and record structs. And they're great for really lightweight value types that have, whether you want true copy by value semantics, which you get by default, or the with syntax is still useful for record structs, but it doesn't need the clone method that is one of the methods generated for just a record when it's a class type to kind of pretend to give copy by value semantics. Structs have that natively anyway, but the with syntax is still possible. And the positional syntax is very neat. It's extremely compact. So what's not to like? I mean, they're great for some things, but there is a bit of a niggle that I have that was described by Martin Fowler. Where did I put my water? As the anemic domain model. And the point that he's trying to make is that so many object-oriented systems can consist of the most basic kind of type, such as the color structure that we saw on the very, well, not the very first slide, but right back at the beginning, just a bag of getters and setters. There is no behavior, there is no, there's nothing rich about that type. It is just a bag of values that can be mutated. And it's common to see types like this where you're using data transfer objects, or what Martin termed POJOs, which in C# terms is a POCO, so it's a plain old Java object or a plain old C# object, where you've got message passing or object to relational mappers. Web controllers is another great example. And the reason it's an anemic model is because all of the logic, all the validation logic, any of the behavior is implemented in the controller rather than within the domain types. And this leads to repetition, brittleness in testing, and brittleness in the design makes them hard to test, in effect. And his real point is that it loses the value of separation of concerns, because you have then a controller with many, many responsibilities. Any kind of sophisticated system will probably have many domain-like types. And having all of the behavior of those types represented in the controller object just leads to these huge monolithic classes with lots of that kind of code in. So we're talking here about value types. So domain types and value types are not the same thing, but there is a relationship between them. So some of the types in a domain will be value types. So color is not an unreasonable example, I think, of that for certain kinds of domain. But the common trope ones like employee or student or class or course, or whatever it is, there is a sense in which they could be implemented as value types. So I make the distinction between data transfer object is a pattern that was also described by Martin Fowler. It has a very specific purpose, and its purpose is to reduce chattiness on a distributed connection. So if you are passing messages, you don't want to be passing millions of color objects in discrete messages. You want one message that passes lots of color objects all in one go, for example. So true data transfer objects don't need a lot of behavior. They don't need to be rich. Their purpose is purely to reduce network traffic commonly. Kind of the same applies for web applications, and to an extent with ORMs, where those types that you are pulling out of the database are dumb. They represent just the data that was in the database. It is within the application that you want to superimpose some kind of richer logic and behavior on those types to turn them into something else. So using DTOs in your application domain leads to the anemic domain model, I think that's the conclusion that is coming here. And similarly, going in the other direction, your value types, you probably don't want to just dump them in a database or send them to a web front end. You need some way of separating the concern between what's visible to the user, say, on a web page, versus what your domain types are inside the application. Inside the application, you're concerned about giving behavior that allows the application to run in an efficient way, but also you are trying to address things like longevity of the code, maintainability, understandability when somebody new comes to it. My point is that records are great when you can just accept the defaults that the compiler gives you. So here I'm going to take a fairly simple value type and critique the idea that the defaults will work for anything. So I'm going to try not to be too rude about C# and its designers, because they have done a pretty good job, even if it really is Java feature envy, But I think I think there is a place for records, and I think they're useful, and especially if you need a very simple type. But very simple doesn't always mean just the one-liner. So here we have a different record using record struct. The same argument would apply for records. This time we're using temperature, and it has a single property called amount. So there are a few problems that I have with this whilst I'm thinking about the anemic domain model and what a domain value type really should be. The first thing is, well, what units is temperature in? It's very difficult to tell from that. Normally, you'd use SI units for something like this. Well, that would be Kelvin. And it depends what you're measuring. So if you're modeling some kind of household thermometer, then Kelvin probably doesn't make sense. Celsius is a bit more sensible for that, okay? So what kind of temperature is it? We can define the units. In a common way of doing it is to have, these are called or the from methods are class factory methods, so they're static methods that return an instance of temperature, but we're encoding the units in the name of the method. So they perform the relevant conversion, and we're saying implicitly that Celsius is the kind of the native units for temperature, and we convert to Celsius when we call the from Fahrenheit static method. So at the bottom, we've got the usage, and we can say from Fahrenheit, from Celsius, and we need a different way to encode our variable names if it matters, but it's normally most important when you're creating instances that you're explicit about the units. It's probably not common to mix and match the units anyway. And then we're still using a positional record, even though we've introduced the curly braces. We can still use the positional syntax, so the compiler still generates a constructor with a single double parameter, and it still creates the amount, although we've renamed it as in Celsius. Sorry, so I've renamed that as in Celsius, so the constructor parameter will be named in Celsius, and the compiler generated property will be in Celsius. So, okay, we can handle units and make it a little bit more obvious. What about data validation? How do we handle out-of-range values? So, minus 1,000,000 Celsius, I think that's definitely go against the laws of physics, as I understand it. So, okay, we need to write a constructor to handle that. And here, again, using expression-bodied syntax and a switch pattern to handle the validation. So, again, relatively new syntax in C#, where the result of the switch pattern is based on the patterns that are matched within it. Any pattern that matches becomes the result of the whole expression. What we're saying here is that if the value being passed in is invalid, then we throw an exception. So there is no result to the expression unless it passes that test. And we use the discard operator, which is only slightly visible on the left, which is a single underbar. It's known as the discard operator, and it matches anything that hasn't already been matched. So if the value being passed in is below 0 Kelvin, we throw an exception. Otherwise, we assign the whole expression the result of the value that was passed in. So we just assign that to the in Celsius property. All good. We can now be sure that we've got, every time we create an instance of temperature, it's at least a valid temperature. I tried to discover if there's a theoretical maximum temperature. And Don would have been a good person to ask, it occurs to me. But as far as I could figure out, there are several. So I decided to avoid the issue. And so the maximum possible temperature is whatever the maximum value of a double is. That's it. Arbitrarily, I'm deciding that here and now. So we could use those class factory methods to do the validation, but that would duplicate effort. And using a constructor for the validation means that we've introduced a class invariant It's not possible to create an out-of-range value of temperature because you get an exception. It won't create the instance. So the rest of your application can be sure any instance of temperature that you have is valid, and that's called a class invariant. It's just a useful one. It's also no longer a positional record. So you may have noticed that the positional parameters have gone. We can't change what the compiler-generated constructor for a record or a record struct is. So if we try to add a constructor that has a single double parameter, it won't compile if it's a positional record, because the compiler will say, you've got two, not allowed. So we have to stop the compiler-generated one and write our own. Doesn't make sense for the compiler-generated one anyway to be there. We've also made the constructor private. So we can't call that we have to use the class factory methods, and thereby we are forcing the users of our temperature type to be always explicit about the units. So because it's no longer a positional record, we have to write our own in Celsius property. Well, that's no big deal. And, okay, we can do different kinds of range validation. So I mentioned earlier about that, a household thermometer. Say you've got some kind of kitchen thermometer for cookery. A valid range might be -40 to +500, and we can express that in a single pattern. Also quite new syntax. Combinatorial, so and or keywords, we can express a range for validation. So some quite neat features there. But now, okay, what about comparing, it's perfectly reasonable for comparing two temperatures to see if they're equal. I would normally, it's commonly held, possibly not. 37 degrees Celsius is 98.6 degrees Fahrenheit, except that it's not, because of floating point comparisons. Inherently imprecise way of representing numbers, and it's, everybody understands that, right? But what we want is some way of expressing, well, almost equal within some reasonable tolerance. What does that mean? We have to write our own equals methods. So the compiler-generated equals method for a record looks as if it's just a read-only struct. It's as if this is what the compiler generates. And it uses this equality comparer of a double. And the equality comparer double dot default returns a type, an implementation of an I-equality comparer interface. Sorry, if you're not keeping up with this, it's fine. Most people don't really have to care. It is that type that uses the I-equitable protocol that I mentioned earlier. So there is some jiggery-pokery actually at runtime to figure out if the T, which is a double in this case, implements I-equitable. Double does implement I-equitable. And so you get the type safe equals when you call dot equals on it. And there are a few special cases, string, bool, an implementation of I-equitable. If it doesn't find any of those things, you just get object equals with whatever that means for your type. And then get hashcode also uses the equality comparer idea. The point being, what we're going to get there is the compiler-generated equals method for our record struct, which just compares each property in turn. There's only one property, the in Celsius property, which is a double, and does effectively a bitwise comparison, and they don't always compare equal. So we need to write our own. Not hard, particularly hard. This is an especially naive implementation of almost equal, where I'm saying, are the two values the same within some fixed number of decimal places? I chose 7 because that makes the test pass. Your mileage may vary. Using it, so obviously, using this way of doing almost equal between doubles it's not the optimum way of doing it, but it does allow me to do it in one line. It becomes extremely unreliable for very, very large numbers. And obviously it's insensitive to differences that are in 8 or beyond decimal places. For a kitchen thermometer, it's probably good enough. So we've already limited the range to -40 to +500. So just saying within 7 decimal places is probably adequate. Has the advantage of being easy to write and efficient enough. Don't take that to mean that's how to compare doubles in every case. So we don't need to also change the other methods generated by the compiler, so in particular the override from object, because that automatically calls this one anyway. So we only need to, and we don't need to explicitly do the I-equitable implementation at the top, because the compiler will do that for us. It just, because we've written our own typesafe equals method, the compiler goes, oh, you've written one, I don't need to bother. But what we've now got, so we've got our own property called in Celsius, we've got our own equals method, we've got our own custom constructor. In fact, we've almost completely overridden everything that the compiler generated for us. So when we had a positional record temperature that was all on one line with the positional parameters, well, we've overridden almost everything that the compiler did. So actually, well, okay, we haven't reduced our typing. So typing is still an issue. Most of the defaults we've decided for this temperature type are not appropriate. Whilst the compiler can generate equals in a sensible way using the equality comparer interface to provide a generic implementation, it cannot do the same for I-comparable. All right, it possibly could, but it doesn't. It doesn't always make sense for 2 objects to be I-comparable. So think about the color type we saw earlier. The compiler could generate effectively less than and greater than for color, just comparing each of the 3 fields. But, I don't know, does blue always compare less than red? Should it? I mean, you know, in a dictionary of English words, definitely it does. But is there one particular way of defining less than for color? I don't think there is. The compiler won't generate it. If it did, I'd probably be quite cross. Because there are other types for which I-comparable makes no sense, or you know, the compiler would almost certainly choose the one that I didn't want. Days of the week. Does Monday come before Sunday? Depends when you define the first day, right? So if we want to be able to sort instances of our type, we have to implement the I-comparable interface. It's not hard to do. We're just comparing doubles, and you know, less than and greater than between doubles is fine, well defined. But we have to do it. We have to write it ourselves. And the wrong button again. And we come back to the default initialization. So when we default, because a record class, actually I should have mentioned that earlier. When record struct came in, record class is its corresponding thing. You just don't have to put the class keyword in. You can if you like, and it's fine syntactically. The default initialization for the plain record, the record class, is not valid because the compiler has generated a custom constructor. We made temperature a record struct, which can always be default initialized. Does that or does that not make sense? Well, it's interesting for temperature because what would happen is that the default initialization of a temperature will default initialize its property, which is a double, and make it 0. But the problem is that 0 Celsius is not the same as 0 Fahrenheit. And because we can default initialize, we are bypassing the class factory methods in which we encode our choice of units. It's a minor thing, but it goes against the vocabulary that we are trying to define for our domain type temperature. So maybe a sealed record for temperature would make more sense, just on the grounds that we cannot default initialize it. That would probably be my choice. But then we, by making it a record instead of a record struct, there are other things that we have to contend with, such as the fact that the methods are all virtual, whether the record is sealed or not. And that has a small but measurable cost. The fact that using the non-destructive mutation, trying not to say that too often, uses a virtual clone method that the compiler implements under the hood for that type. Again, it's tiny but measurable cost. So there are trade-offs between records and record structs that might not be immediately obvious. So the defaults work just fine for some types. Color, a default initialized color is black. Just is. That's it. Everything set to 0, it's black. And it's fine. So where it becomes difficult is where, temperature is one of those special cases where 0 might not mean 0. When you have properties within a type that are reference types, then they can be null. If the type can be default initialized, you have to worry about null. It's just another thing. It's a way, it's one more thing to think about. Does default initialization make sense for the type that I'm trying to represent? So records are great, I think, a great way of defining the perfect anemic type. There is behavior, but it's nice to implement ourselves occasionally. But if we need to override all of those compiler-generated things, then we may as well just use a struct or a class. So that I think that there is still space in C# for just the humble struct. But especially when, floating point or reference type fields, if we don't need to sort them, we don't care about default initialization. The names of the parameters, we can fiddle with those. The positional record syntax is a very compact way of defining a type that has quite sophisticated value semantics for both equality comparisons and for copying via the with syntax, non-destructive mutation. So that's me. That's everything I had prepared. Thank you. Any questions? So the question is default initialization just terrible? Yes. In short, yes. I mean, it's been a bugbear in C# since the very beginning. It was one of those optimizations for value types that the compiler can just black the memory because they don't. So heap-based objects have their memory blatted at runtime, and non-heap-based objects, wherever they may be, although in practice they are 0 initialized, but the language designers go to great lengths to stop you understanding that. But because you can always, so the thing about a struct is you don't have to call a constructor on it in order to create an instance. If it's got public fields, you can create an uninitialized instance of a struct and then assign value. As long as you assign a value to all of its fields, it's a valid object. And yes, it's awful. It's genuinely appalling, but it's, one of those optimizations provided by the compiler it's really a non-optimization. So the question is it confusing to have very similar but not exactly the same data structures, or they're not sufficiently different I think, implied in the question. And again, in short, yes. And that's partly the point of why I put the talk together, right? Is to try and explore what the differences are, to highlight ones that really would be non-obvious to me had I not actually spent time digging on it. Particularly, there is one that I missed out, actually. There is another difference between record classes and record structs, is that a record struct, by default, has publicly mutable properties, unless you explicitly mark it read-only. A record class, by default, has publicly immutable properties, and you cannot make them mutable unless, other than by writing it yourself. So anything that you write in a record or record struct just stops the compiler putting one in. So you can make a mutable record, but you wouldn't, because value types, it's supposed to be a value type. It's specifically designed to be a value type, except that the default for record structs is a public setter. Yeah, I mean, it's just the wrong decision. So that is, another little difference I should have mentioned on the way. So, okay, the compiler will generate loads of things, but I think it's important to be aware of those differences, and they are non-obvious. So, yeah, confusing might be slightly the wrong word, but I can imagine people new to the language or new to the features going, well, do I do it? So, you know, as I said at the beginning, I thought I finally got a handle on choosing between class and struct in a way, you know, there are some guidelines online in the Microsoft documentation which I don't agree with on that choice. There are other things at play. But I thought I'd finally decided, and then they came along and changed the whole thing. So yeah, have to agree.